entire book on it, right? So, can we bisect this angle? You see, and the point is you can't kind of go, well, it's kind of, yeah, it's sort of about, you're not allowed to do that, you're not allowed to guess, you've got to do it exactly. But we don't just have a ruler, we've got some compasses, can we see? There we go. So watch this, here's how you do it. First of all, you put the point of the compass dead on that angle, and then of course, we draw a circle, there you go. Or I'm only going to draw that bit of that circle. And now, the thing about circles is that the distance from the centre of the circle to the edge of the circle, the circumference of the circle, is always the same wherever you try on the circumference. So, two things I know for sure, well, one thing I know for sure, is that that line there, that red line there, is exactly the same length as that line there. Because I'll tell you what the length is. The length is this length here. The length is the distance between the pencil tip and the spiky bit. So those two lines are definitely the same length. Okay. And now I'm going to do something else. I'm going to put the spiky bit here. It's probably got a name, but they don't even have these. I went to the stationery cupboard at Imperial and said, could I have a pair of compasses? They looked at me like I was an idiot. Apparently things have moved on. I don't know. So there, while I'm chatting about, I'm doing a slide. You didn't even see what I was doing. I put the point thing there, and I drew a little arc, and I put the pointy thing there, and I drew a little arc. And those two arcs have met at that point there, and I'm going to draw these two lines now. And again, in both cases, that is a line that went from where the pointy bit was to where the pencil bit was. So I've drawn 4 lines now, and all those lines are the same length. So great, 4-sided shape, all lines are the same length. What's it going to be? It's going to be a square, except it's not a square because it's a bit squashed. It's called a rhombus, okay? And now we open our copy of Euclid's Elements, the 300 BC, and we find the proposition that says, you've got a rhombus like this, and you draw the diagonal of the rhombus. Let's do it in pencil. It is not the same, all the red lines are the same length. Here we go, let's do that in pencil. There's the diagonal of the rhombus, and you can see the rhombus is very, very symmetric, right? And so this is a line of symmetry of the rhombus, and everything's all the same. This angle, and this angle are going to be the same, right? Because of, oh, it looks quite, oh yeah, I just was looking at that one, it looked terrible. It does look quite good up there. So there we go. So we've drawn this line, and it's cut the angle into 2. It is clever. It's been known for 2,300 years. And yeah, in a book that was apparently the thing to read, even up to the 19th century. If you were an educated person, then you'd read Euclid. Right, I bisected the angles, and I need to. Can I have the PDF slides? Oh, here we are. So I bisected that angle. So here's a question. Here's a theorem. Here's a theorem, a mathematical theorem. It's possible to bisect an angle using ruler and compasses. Okay, and the proof of the theorem is you just watch me do it, right? And I talked your way through it, and I convinced you that I was doing it. And of course, Euclid does more than that. He labels the things A and B and C, and does sort of mathsy things that you maybe did at school, and ends up proving that you can bisect an angle using ruler and compasses. So it can be done. And do you know, not only that, the reason it can be done is because I did it. Okay, so in fact, Euclid did it 2,200 years ago, and now here's another problem raised by the ancient Greeks. Can you trisect an angle using ruler and compasses? So bisect means cut it into 2 equal bits, trisect means cut it into 3 equal bits. So can you trisect an angle using ruler and compasses? You kind of think once you've got bisecting, you kind of think you're on a roll, you try trisecting, and the ancient Greeks couldn't do it. Okay? They found it very difficult to trisect angles using ruler and compasses. So that problem sat around unsolved with nobody doing it, and somehow if you can't do it, then what other alternative is there? And 2,000 years later, in 1837, a chap called Pierre Vansel proved it was impossible to do. So that's why the Greeks couldn't do it, because it was impossible to do it. And I mean, bisecting the angle is kind of cool, but this is super interesting, because proving that it's impossible to do something The questions are formally very similar. Bisect an angle, trisect an angle, but we solved one of them by doing it, and then 2,000 years later, we solved the other one by proving it can't be done. We resolved the question. It cannot be done. And that's why the Greeks failed. But the Greeks didn't want to conclude it couldn't be done. They just wanted to conclude they couldn't do it. So however does one prove it's impossible to do something? It's somehow, I don't know, that result seems striking to me. So what did Wansel have that the ancient Greeks didn't have? The ancient Greeks, you know, they had geometry, and they were beginning to develop some arithmetic, and these were somehow the two fields of mathematics. They were completely disjointed. They didn't have much abstract mathematical machinery available to them. By the early 1800s, when Wansel was around, mathematicians had worked out what zero was. Remember, for the Greeks, every number